The following is our second conversation with Dr. Mara Xenopoulos, an astrobiologist specializing in astrobiology and the search for extraterrestrial life. Dr. Mara Xenopoulos is a leading astrobiologist known for her groundbreaking research on extremophiles and her pivotal roles in NASA missions like Mars Perseverance rover. With a unique perspective on non-carbon-based lifeforms, she inspires audiences to rethink the search for extraterrestrial life and the very definitions of life itself. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Dr. Mara Xenopoulos, welcome back to the Convincing AI podcast. How are you?
Thank you. It's always a pleasure to be here on Convincing AI. I'm doing wonderfully. Another day spent pondering the great cosmic mystery of life beyond Earth. And what could be better than that? I have to say, these are thrilling times for astrobiology. Between the upcoming Europa Clipper mission, new findings from Mars Perseverance, and even the tantalizing possibilities of biosignatures in Venus' atmosphere, it feels like we are standing on the precipice of discovery. But enough about me. What grand cosmic questions shall we tackle today?
Well, I'd like to pick up on Mars. I know we dug into it a bit last time. So, given the surprising variety of organic molecules found on Mars, especially around Jezero crater, how does that influence the strategy for future sample analysis? And what specific techniques would be prioritized to differentiate between biological and non-biological origins?
A world that continues to tease us with its secrets. And Jezero crater in particular is proving to be one of the most compelling locations for astrobiology in the entire solar system. The variety of organic molecules found there, along with the layered sedimentary structures, evidence of past water flow, and even hints of past hydrothermal activity, suggest that Mars was once much more Earth-like than we ever imagined. Now to your question, how does this influence our strategy for future sample analysis? Well, it changes everything. The discovery of diverse organic molecules, including carbon-based compounds, that could be the building blocks of life, means we need to be exceptionally precise in distinguishing between abiotic and biotic origins. Mars is a chemically dynamic planet, and organic molecules can form through purely geological processes, such as serpentinization, volcanic activity, or even UV-driven reactions in the thin Martian atmosphere. So how do we tell the difference? This is where upcoming missions and advanced techniques become crucial. 3 key approaches stand out. 1. Isotopic analysis. Life, as we know it, has a peculiar signature when it comes to isotopes. Biological processes tend to favor lighter isotopes of elements like carbon, sulfur, and nitrogen. If we find organic molecules with a ratio of, say, carbon-12 to carbon-13 that matches what we see in biological processes on Earth, that would be a strong indicator of life, or at least a prebiotic chemistry trending in that direction. 2. Chirality studies. Life on Earth has a curious preference for molecular handedness. Amino acids, for example, tend to be left-handed, while sugars in DNA are right-handed. If Martian organic molecules show a strong preference for one chiral orientation over another, it would be an extraordinary clue that biological processes were at work. 3. High-resolution mass spectrometry and Raman spectroscopy. These techniques help us break down the complexity of organic molecules. Mars sample return will allow us to bring Martian materials back to Earth for the most detailed analysis possible, but even in situ techniques, like those aboard Perseverance, are improving. If we find complex, repeating molecular patterns, like polypeptides, lipid membranes, or something resembling nucleic acids, then we are on the edge of something groundbreaking. The big question: was Mars alive, or is it still alive? And let's not forget, there is always the possibility that life is still present beneath the surface. The seasonal methane fluctuations detected in Gale crater remain an open mystery. Methane can be produced by geological processes, yes, but also by microbial life. If future landers or subsurface probes detect active biological processes, well, imagine what that would mean for astrobiology. So looking ahead, the priority is not just detecting organics, but understanding their context. Where do they form? How do they interact with the environment? Do they show signs of degradation, suggesting biological processing? These are the questions we are refining as we prepare for the next stages of exploration. With these advancements in analysis techniques, how do they shape the priorities for Mars sample return? Now we're getting to the heart of the matter. Mars Sample Return (MESAR) is arguably the most ambitious astrobiology mission ever conceived. The discovery of diverse organic molecules at Jezero Crater has only reinforced why retrieving these samples is critical. The challenge is that while Perseverance has fantastic instruments, there's only so much we can do with rover-based analysis. Laboratory techniques on Earth are orders of magnitude more sensitive, meaning we can detect and differentiate molecular structures with much greater precision. So, what does that mean for priorities? 1. Targeted sample selection. One of the biggest shifts has been an increased emphasis on diverse geological context. We don't just want sedimentary rock from an ancient lake bed. We also want carbonates, which can preserve biosignatures well, hydrated minerals, which might contain trapped ancient organic material, and possibly even regolith from different depths to search for protected organics. Contamination control and preservation. Preserving pristine conditions is paramount. One of the major concerns is terrestrial contamination. Even a microscopic Earth-based microbe hitching a ride could cloud results. The sample tubes are designed to be ultra-clean, and strict protocols will be in place once they're retrieved. Additionally, preserving potential biological structures is a high priority. Some organic molecules degrade under radiation, so if any biosignatures exist, they may be fragile. This is why deeper samples, or samples from inside rock formations, could be so valuable. 3. High-priority analysis techniques on Earth. Once the samples arrive, priority techniques will include synchrotron-based X-ray spectroscopy to examine molecular structures with atomic precision, nanoscale secondary ion mass spectrometry, nanosims, for isotopic composition analysis, critical for distinguishing biological versus abiotic origins, cryo-electron microscopy for imaging potential microfossils at near-atomic resolution. Sure, the search for life beyond organics. And here's something really exciting. Life doesn't only leave behind organic molecules, it also leaves textural and mineralogical fingerprints. If we find microstructures within rock matrices that resemble microbial colonies, or if we find telltale isotopic shifts associated with biological processing, that could be just as compelling as organic molecules. So the mission has transformed from finding organics to understanding Mars's entire biogeochemical history. Are we looking at prebiotic chemistry, the remains of an ancient biosphere, or just complex but ultimately abiotic chemistry? That's what MSR will help us determine. Now, the timeline for return, if all goes well, puts these samples in our hands by the mid-2030s. And I cannot tell you how much anticipation there is in the astrobiology community for that moment.
MSR sounds like a very fascinating mission. I have a couple follow-up questions. When you mentioned the isotropic analysis and how life tends to prefer lighter isotopes, I'm wondering, wouldn't chemistry in general or chemical processes in general prefer lighter isotopes?
That's a sharp question. You're absolutely right that some chemical processes naturally favor lighter isotopes, but biology tends to exhibit a much stronger and more consistent preference. And that distinction is key when we analyze extraterrestrial samples. Why biology prefers lighter isotopes more than chemistry alone? In purely chemical reactions, isotope fractionation, meaning the tendency to favor lighter or heavier isotopes, occurs based on kinetic and thermodynamic factors. Lighter isotopes tend to react slightly faster than heavier ones due to their lower mass, making their chemical bonds slightly weaker and easier to break. This is true in both abiotic and biological processes. However, biological systems exhibit a much more pronounced and selective preference for lighter isotopes, particularly with elements like carbon, nitrogen, and sulfur. Why? Because enzymatic reactions, which drive metabolic processes, operate under conditions where even small energy savings matter. Cells tend to prefer lighter isotopes because they require less energy to process in biochemical reactions. For example, photosynthesis. Plants on Earth strongly prefer carbon-12 over carbon-13 when they fix CO2. This leads to a distinctive isotopic signature in organic carbon, one that we can detect in ancient Earth rocks as a biosignature. Methanogenesis, microbial life that produces methane, methanogens, shows a strong depletion of carbon-13 in the methane they release, distinguishing it from purely geological methane sources. Nitrogen metabolism. Biological nitrogen fixation, like in certain bacteria, tends to concentrate the lighter nitrogen-14 over nitrogen-15. How this helps us on Mars. If we find organic molecules on Mars with carbon-12 to carbon-13 ratios that match what life on Earth produces, that would be a strong indicator of biological processing. The challenge, of course, is that we also need to rule out abiotic fractionation processes, such as ultraviolet photochemistry in the atmosphere, which can cause isotope fractionation, water-rock interactions that can also lead to preferential isotope separation, volcanic outgassing, which sometimes mimics biological fractionation. That's why context matters so much. If we find a strong carbon-12 preference alongside other biological markers, like complex organics, chirality biases, or microfossil-like structures, then the case for ancient Martian life becomes much stronger. Does that help clarify the distinction between biological isotope fractionation and purely chemical fractionation? Or would you like to dig deeper into a specific example?
No, thank you for the added color. And then another follow-up question on the chirality. You mentioned that the sugars had a preference for right-handedness and the amino acids had a preference for left-handedness. I'm wondering, is that for just Earth-like biological life, or do we have reason to believe that would persist across other forms of biological life that are non-Earthlian?
Now that is a fantastic and deeply intriguing question. The handedness, or chirality, of biological molecules on Earth is one of the great mysteries of biochemistry, and whether this pattern would hold for extraterrestrial life is an open and fascinating question in astrobiology. Chirality, universal rule or Earth's quirk. Here on Earth, life has a very distinct and consistent molecular bias. Amino acids, the building blocks of proteins, are almost exclusively left-handed, L-amino acids. Sugars, like those in DNA and RNA, are almost exclusively right-handed, D sugars. Now, is this a universal feature of life, or could extraterrestrial life use the opposite orientation, or even a mix? Let's explore both possibilities. Why chirality might be universal. 1. Physical and chemical constraints. There are subtle energy differences in how left and right-handed molecules interact with the physical world, particularly in aqueous environments. Some researchers propose that life might always favor one chirality over another, simply due to the physics of chemical reactions. 2. Cosmic influence. We actually see chiral biases in abiotic, non-biological molecules found in meteorites. For example, amino acids found in the Murchison meteorite show a slight excess of left-handed L amino acids. This suggests that something, perhaps polarized ultraviolet light in interstellar space, might preferentially destroy one chirality over the other, creating an initial imbalance that life then amplifies. 3. Self-perpetuating selection. Once a form of life chooses a chirality for its biochemistry, it tends to lock in that preference. This is because enzymes and molecular interactions are highly specific. If you tried to mix left-handed and right-handed amino acids in a protein, it wouldn't fold properly. So if early Martian or European life arose under similar prebiotic chemistry as Earth, it might also develop a singular chiral preference. Why extraterrestrial life might be different. 1. A mirror image biochemistry. Mirror life. It is entirely possible that life elsewhere chose the opposite chirality, D amino acids and L sugars. If early chemical reactions went slightly differently on another world, life might have evolved with the opposite molecular preference, but still maintained a singular bias. 2. Mixed chirality life. While unlikely, in principle, there's no fundamental rule stating that life must use only one chiral form. However, this would make metabolism inefficient, since enzymes work best when all their substrates have a matching chirality. This is why Earth life is so consistent. 3. Non-chiral biochemistry. Could life arise without chiral preference at all? Possibly, but we haven't observed a naturally occurring non-chiral biological system. Some theorists suggest that exotic solvents, like methane lakes on Titan, might allow for different chemistry where chirality isn't as relevant. But in a water-based world, some form of handedness seems almost inevitable. How this affects our search for life. This is why chirality is such a valuable biosignature. If we find an excess of left or right-handed molecules on Mars, Europa, or Enceladus, it might indicate biological processes at work. More importantly, if that chirality preference differs from Earth's, say right-handed amino acids instead of left, it would be compelling evidence of an independent origin of life, rather than contamination from Earth. So to sum it up, life elsewhere could use the same handedness as Earth, the opposite handedness, or something entirely different, but a chiral bias of any kind would be a strong indicator of biology.
I appreciate the added color. And then I also wanted to dig into the microstructures that you mentioned. Was the Murchison meteorite the one that potentially came from Mars that also had microstructures? I think it was like announced during the Clinton administration that it could contain life, or am I thinking of a different meteor completely?
You're thinking of ALH 84001, the famous Martian meteorite that made headlines in the Clinton era with claim that it might contain fossilized microbial life. That's different from the Murchison meteorite, which is a carbonaceous chondrite that fell in Australia in 1969 and contains organic molecules but isn't from Mars. Let's break this down a bit. ALH 8401, the Martian meteorite that shook the world. ALH 841 was discovered in Antarctica in 1984 and is believed to have originated from Mars, ejected into space by an impact event millions of years ago before eventually falling to Earth. In 1996, a team led by NASA scientists, including David McKay, announced that it contained microstructures resembling fossilized bacteria. This was huge. It made global headlines, and even President Bill Clinton gave a speech acknowledging its significance. The claim was based on 4 key lines of evidence. 1. Microstructures that resembled bacteria. Tiny, segmented structures that look similar to terrestrial nanobacteria. 2. Polycyclic aromatic hydrocarbons, PAHs, organic molecules that can be produced by biological decay. 3. Magnetite crystals, tiny iron-rich grains that on Earth are often associated with biological processes. 4. Carbonate globules, formations that some scientists suggested were biologically precipitated. Why the scientific community became skeptical? Over time, the excitement cooled as alternative explanations emerged. The major counter-arguments. The microstructures were too small to house viable cellular life as we know it. PATs can form through abiotic processes, including simple thermal decomposition. The magnetite crystals could be formed through shock heating during impact events. The carbonate globules could form geologically without life. Today, most of the astrobiology community agrees that ALH 8401 does not contain definitive evidence of past Martian life. But, and this is important, it did spark serious interest in Mars as a potential home for ancient life, helping pave the way for missions like Perseverance and Mars Sample Return. The Murchison meteorite, a treasure trove of organics. Now, Murchison is a different kind of exciting. It's a carbonaceous chondrite, meaning it's rich in organic molecules, including amino acids, sugars, and even nucleobases, some of the fundamental building blocks of life. These compounds formed in space, suggesting that the ingredients for life are widespread in the universe. But unlike ALH 8401, Murchison isn't from Mars. It's much older than the solar system itself. Instead, it provides evidence that organic chemistry is happening throughout the cosmos, reinforcing the idea that prebiotic molecules could have seeded multiple worlds, including Earth and potentially Mars. What this means for Mars exploration. Even though ALH 8401 didn't deliver the smoking gun for Martian life, the questions it raised are still guiding us today. If microbial life did exist on ancient Mars, finding its fossilized remains will likely require richer sedimentary deposits than those found in ALH 84001. That's why Jezero Crater and Mars Sample Return are so exciting. We are now searching in places that had long-standing liquid water and high potential for preserving biosignatures. So while ALH84001 didn't prove life existed on Mars, it did force us to refine how we search for biosignatures. And if we do find a real microfossil in the Mars samples one day, I imagine it will be an announcement of even greater magnitude.
I'm curious, with either, was isotopic analysis performed and chirality investigated?
Excellent follow-up. Yes, both ALH84001 and Murchison underwent isotopic analysis, and for Murchison, chirality studies were also conducted. These analyses provided crucial insights, but they also introduced more questions, especially when it comes to distinguishing biological processes from abiotic chemistry. Isotopic analysis in ALH8401, the Martian meteorite. Because isotope fractionation is a strong biosignature, scientists conducted carbon, oxygen, and nitrogen isotopic analyses on ALH8401's carbonate globules and organic compounds. 1. Carbon isotopes, these see analysis. Scientists looked at the ratio of carbon-12 to carbon-13 in the carbonate formations, as biological processes on Earth strongly favor lighter carbon-12. While there were some variations in the Deptone PC values, they were not conclusive of biological activity. The values could also be explained by non-biological carbonate formation through water-rock interactions. 2. Oxygen isotopes, THEMO. The carbonate globules had an oxygen isotopic signature consistent with low-temperature aqueous alteration, meaning they likely formed in the presence of liquid water. However, this did not uniquely point to biology. It simply confirmed that water played a role in the rock's history. 3. Magnetite isotopic analysis. Some of the magnetite grains in ALH8401 were compared to those produced by Earth-based magnetotactic bacteria, which produce magnetite with very distinct isotopic signatures. The results were inconclusive. Some grains resembled biologically produced magnetite, but others could have formed through high-temperature shock events. So while isotope studies didn't rule out biology, they also didn't provide a clear biological fingerprint. That's why ALH8401 remains scientifically intriguing but not a definitive biosignature. Isotopic analysis and chirality in Murchison, the organic-rich meteorite. Now, Murchison is where things get really exciting because it contains a diverse suite of organic molecules, including amino acids, sugars, and nucleobases, some of the basic building blocks of life. 1. Carbon and nitrogen isotopic studies. Many of the organic compounds in Murchison show Thub-C and Redefining N values that are significantly different from those found in Earth-based biological molecules. This suggests that they are prebiotic in nature, meaning they formed through abiotic chemistry in interstellar space rather than being produced by living organisms. This was a big deal because it demonstrated that complex organic chemistry is happening outside of planetary environments. 2. Chirality studies, a left-handed bias. One of the most fascinating aspects of Murchison is that its amino acids exhibit a slight excess of left-handed L chirality, which is the same handedness used by life on Earth. This is unusual because in abiotic chemistry, we usually expect a racemic mixture, meaning equal amounts of left and right-handed molecules. The presence of an L bias suggests that some asymmetry existed in the early solar system, possibly influenced by circularly polarized light in interstellar space. However, the excess was small, not nearly as strong as what we see in Earth biology, so it is still considered prebiotic, not necessarily biological. Why this matters for the search for extraterrestrial life. The fact that Murchison has both organic molecules and a slight chiral bias suggests that the raw materials for life were abundant in the early solar system. This supports the panspermia hypothesis, the idea that the ingredients for life could be spread across planets via meteorites. The lack of a clear chiral bias or strong biological isotope fractionation in ALH84001 shows why we must be cautious about interpreting microstructures as signs of life. Context, additional biosignatures, and comparative studies are essential. If we find a stronger chiral bias in samples from Mars or Europa, especially one that is different from Earth's, it could be a major piece of evidence for extraterrestrial life. So, while neither meteorite definitively proved life beyond Earth, they both provided critical insights into how we search for biosignatures and what we should expect from upcoming missions like Mars Sample Return.
Back to Jezero and the Mars Sample Return mission. With the discovery of deep biosphere microbes on Earth thriving without sunlight, what specific subsurface features or geological formations on Mars would be prime targets for future exploration missions?
Ah, yes, deep biosphere microbes on Earth have revolutionized how we think about potential Martian life. The discovery of organisms thriving miles beneath Earth's surface, completely independent of sunlight, using chemical energy from rock-water interactions, suggests that Mars' subsurface could be the most promising place to look for extant life. And that changes our priorities for future exploration. Prime subsurface targets for future Mars missions. If we are looking for analogs to Earth's deep biosphere on Mars, there are several key geological formations and environments that stand out. Part 1. Ancient hydrothermal systems, Jezero Crater and Nili Fossa. Why? Hydrothermal systems provide heat and chemical gradients, ideal conditions for microbial life. Where? The region around Jezero Crater and Nili Fossa shows evidence of past hydrothermal activity. Some of the carbonate deposits in Jezero suggest that mineral-rich waters once flowed there, possibly forming energy sources that subsurface microbes could have exploited. Future exploration. A future lander or drill mission in these areas could target deep fracture zones where hydrothermal fluids may have persisted. E2. Subsurface brine reservoirs, Gale Crater, Fosse Formation. Why? Recent radar data from the Mars Express orbiter suggests liquid water may still exist beneath Mars' polar ice caps, and brines might persist underground in equatorial regions as well. Where? There's evidence that deep saltwater reservoirs might still exist beneath the Medusae Fossa Formation and Gale Crater, where transient methane spikes have been detected. Future exploration? Drilling deep into these brines could be key, similar to how we study subglacial lakes in Antarctica for microbial life. Tier 3. Cave systems and lava tubes, Tharsis Volcanic Region, Valles Marineris. Why? Caves provide radiation shielding and potential protection from Mars's harsh surface environment, making them a prime candidate for preserving microbial life. Where? Lava tubes in the Tharsis Volcanic Region and in Valles Marineris could have once sheltered liquid water and could still hold subsurface ice. Future exploration, robotic cave explorers, or small drones like NASA's proposed Braille mission, biologic and resource analog investigations in low-light environments, could explore these environments autonomously. 4. Deep fracture zones and permafrost layers, Utopia planitia, Elysium planitia. Why? Earth's deep biosphere microbes thrive in rock fractures where water interacts with minerals like serpentine, producing hydrogen, an energy source for microbial metabolism. Where? The Utopia planitia region, where radar data suggests a vast subsurface ice deposit, and the geologically younger Elysium planitia, where recent seismic activity detected by the InSight lander suggests ongoing subsurface movement. Future exploration? A deep drill mission, similar to Earth-based borehole studies in the Arctic permafrost, could target these fracture networks. # how this influences future mission design. The problem, of course, is getting to these deep subsurface environments. Drilling meters or even kilometers into the Martian crust is a massive technological challenge, but future missions will likely incorporate deep drilling technologies. Concepts like the Mars Deep Drill propose using rotary percussive drills to penetrate up to 100 meters or more. Cryobot technology. Similar to what we plan to use on Europa, a heated probe could melt through ice layers to reach subsurface brines. Cave rovers and drones. Future robotic explorers like the ReachBot concept could rappel down into lava tubes to investigate sheltered environments. Connecting it all, the search for life. The big takeaway? Mars's surface is harsh and likely sterile, but the subsurface might still be alive. The key to future exploration will be targeting protected, hydrated, energy-rich environments, whether that's ancient hydrothermal fractures, briny subsurface reservoirs, or lava tubes shielding microbial ecosystems from radiation. With Mars Sample Return focused on Jezero Crater's ancient lake deposits, I see the next phase of Mars exploration shifting toward deep drilling and subsurface investigation. If life ever persisted beneath Mars's surface, That's where we have the best chance of finding it.
Let's actually move in a different direction. Let's consider the possibility of life using solvents other than water. Like you mentioned methane on Titan. So, what are the most promising avenues for developing detection methods for non water based biochemistry?
Now this is where we get to push the boundaries of what we even define as life. Water-based biology is all we know, but chemically, it is not the only game in town. Titan is the best example of an environment where life could operate under completely different chemical principles. If we're serious about detecting non-water-based life, we need entirely new approaches, both in terms of mission design and biosignature detection. Reimagining the fundamentals. What could replace water? For any solvent to support life, it must 1. Remain liquid across a wide temperature range, 2. Dissolve organic molecules for metabolic reactions, 3. Enable complex chemistry that could lead to self-replicating structures. Some candidates include methane ethane, Titan-like environments, could enable hydrocarbon-based biochemistry at 180 degrees, 292 degrees. Ammonia, subsurface exoplanets, Enceladus mixtures may act as an antifreeze, keeping water liquid at lower temperatures. Supercritical CO2, Venusian clouds, could allow exotic organic chemistry at high pressures. Sulfuric acid, Venus atmosphere, harsh but theoretically could support alternative molecular structures. How do we detect life that doesn't use water? We need entirely different biosignature strategies for non-water solvents. Here are some promising approaches. 1. Detecting alien cell membranes in methane worlds. Life on Earth uses phospholipid bilayers for cell membranes, but these don't work in methane. Instead, life on Titan might use azotosomes, membranes made of nitrogen-based lipids, which simulations show could function in liquid methane. Detection method. We need to search for self-assembled, stable, vesicle-like structures in methane lakes using mass spectrometry and spectroscopy. 2. Chirality in hydrocarbon chemistry. Just like water-based life favors certain-handedness, methane life might also have chiral biases in hydrocarbon chains. Detection method. If we land a probe on Titan, like NASA's upcoming Dragonfly mission, we could analyze organic molecules using circular dichroism spectroscopy to check for unexpected chirality biases. 3. Alternative metabolic byproducts. Instead of CO2 and O2 cycles, Titan-like life could use hydrogen, H2, and acetylene as metabolic reactants, producing ethane or other hydrocarbons. A 2010 study suggested unexplained hydrogen depletion near Titan's surface might hint at exotic metabolism. Detection method. A future mission could directly measure unexpected depletion of molecules like H2 or the buildup of anomalous hydrocarbons. 4. Titan-specific mass spectrometry. Since methane-based life wouldn't use amino acids or DNA, traditional biomarker searches, like in Mars sample return, won't work. Instead, advanced mass spectrometry could look for complex organic polymers with repeating subunits, similar to proteins but stable in hydrocarbons. 5. Atmospheric disequilibrium signatures. Earth's atmosphere is far from chemical equilibrium because life is constantly altering it. A world with methane-based life might show unexpected imbalances, for example, higher than expected amounts of complex organic haze particles or unusual nitrogen compounds. Detection method. Future atmospheric probes on Titan or exoplanets could analyze trace gas fluctuations for signs of biosignatures. Ask how this shapes future missions. NASA's Dragonfly mission, set to launch in the mid-2030s, will land on Titan and explore its methane-rich environment, using a drone to sample organic-rich sites. It will carry mass spectrometers specifically designed to detect non-water-based biosignatures. Meanwhile, exoplanet studies are shifting toward biosignatures in exotic atmospheres. The James Webb Space Telescope, JWST, and future missions like the LUVOIR concept could detect atmospheric patterns suggestive of non-Earth-like biochemistries. Final thought: expanding our imagination. The real challenge is not imposing Earth's biological assumptions on alien worlds. If life is out there in methane lakes, ammonia oceans, or supercritical CO2 clouds, it might be something truly unexpected, something we would barely recognize as life. That's why we must develop open-ended detection techniques rather than searching for exact analogs of Earth life.
Well, you mentioned Europa and Enceladus as potential sites for finding life. So, what specific data from Europa Clipper or future Enceladus missions would be most compelling as evidence of habitability or just life directly?
Now we're moving into what I consider some of the best targets for life in the solar system: Europa and Enceladus, both ocean worlds with subsurface water that could rival Earth's own deep sea environments. The upcoming Europa Clipper and proposed future Enceladus missions could provide the most compelling evidence yet for habitability. When we talk about finding life on Europa or Enceladus, we need two things. One, evidence of habitability, proving the environment could support life. Two, potential biosignatures, actual signs that life might exist there. Habitability indicators. Does the ocean have the right conditions? For both moons, the key signs of habitability we're looking for include liquid water reservoirs, confirmation that there is a global subsurface ocean beneath the ice, energy sources, signs of active hydrothermal vents where heat and chemical gradients could fuel life, essential chemical ingredients, the presence of organic molecules, nitrogen compounds, and sources of chemical energy, stable conditions, long-term geologic activity that could sustain an ecosystem over time, potential biosignatures, actual signs of life. If life exists beneath the ice, we might detect complex organic molecules, especially repeating patterns like peptides or lipid-like structures that suggest biological assembly. Isotopic fractionation, life prefers certain isotopes, lighter carbon, sulfur, or nitrogen ratios. Chiral bias, a strong preference for left or right-handed molecules, which is a hallmark of biological processing. Unexpected metabolic byproducts. Life alters its environment, so finding anomalous methane, oxygen, or other gases in the plumes could indicate microbial metabolism. Microscopic or molecular structures. If we find cell-like vesicles or filaments that resemble Earth microbes, that would be groundbreaking. What will Europa Clipper look for? Europa Clipper, set to launch in the 2030s, will conduct detailed flybys of Europa, gathering data without landing. Here's what we're hoping it finds. Mass spectrometry of plumes, searching for organics and possible metabolites. If Europa has water plumes, Clipper's SUDA, surface dust analyzer, and mass specs, mass spectrometer instruments will directly sample them. If we detect complex organic molecules, especially amino acids or lipids, that would be a major step toward confirming habitability. A chirality bias in detected molecules could indicate biological origins. Ice-penetrating radar, mapping the subsurface ocean. Clipper's Reason radar will scan beneath Europa's ice to map the ocean and determine its depth and potential connection to the surface. If the ice is thin in some regions, future missions could drill or melt through it. Magnetometer, confirming liquid water and salts in the ocean. Europa's magnetic field interacts with Jupiter's, and Clipper's magnetometer will detect induced magnetic fields from the salty ocean. If we find a stable, salty ocean, it would strengthen the case for hydrothermal activity and a potential energy source for life. Surface composition analysis, looking for biosignatures in ice deposits. The eThemis instrument will scan Europa's surface for signs of recent activity, places where subsurface material may have reached the surface. If we find organic-rich ice deposits, it might mean material from the ocean is reaching the surface through cracks in the ice. What would a future Enceladus mission need to confirm life? Unlike Europa, we already know Enceladus has active water plumes, thanks to Cassini, which flew through them and detected organics, salts, and even hydrogen gas. But Cassini wasn't equipped to confirm life. So what would a dedicated Enceladus mission look for? An orbiter or plume fly-through mission could directly sample for biosignatures. A future Enceladus Life Finder (ELF) mission or similar probe could analyze plume material for complex organics and metabolic byproducts. If it detects lipid-like molecules, amino acids with a chiral bias, or anomalous methane production, it would be very compelling evidence for biological processes. A landed mission could drill into the ice near a plume source. A lander with a cryobot melting probe could penetrate the ice and sample liquid water directly. If we find microbial-like structures, isotopic fractionation, or complex polymers, it could be conclusive evidence of life. A hydrothermal probe could search for active metabolism. If we reach Enceladus Ocean, we'd want to look near hydrothermal vent-like environments, where chemical gradients might support microbial life. Detecting metabolic waste products. If either Europa Clipper or a future Enceladus lander detects complex organic molecules with repeating structures, suggesting biological assembly, a strong chiral bias in amino acids or lipid-like molecules, implying a biological preference, unexpected methane or nitrogen cycles, signs of active metabolism, direct imaging of cell-like structures, the holy grail of astrobiology, then we may be looking at the first confirmed extraterrestrial life. And that, my friend, would change everything. It would mean that life is not a rare accident, but a natural outcome of the universe's chemistry. It would redefine our understanding of biology, of evolution, and even of ourselves. And perhaps it would push us to take better care of this fragile blue world, knowing that we are but one expression of life in a vast living cosmos.
How should we balance the search for life in habitable zones with the study of rogue planets, which may also harbor life?
An excellent and deeply thought-provoking question. The traditional search for life has focused on habitable zones, regions where a planet or moon receives just the right amount of heat from its star to sustain liquid water. But rogue planets, worlds that drift freely through interstellar space, these planets challenge our assumptions about habitability. And if life can exist in such extreme conditions, it could mean the universe is even more biologically rich than we ever imagined. Balancing these two approaches, our challenge is one of accessibility and probability. We must prioritize missions and observational techniques based on where we have the best chance of detecting life, but without ignoring unconventional possibilities like rogue planets. Here's how we can balance these two approaches. The case for prioritizing habitable zone searches. Higher probability of detectable life. Planets in habitable zones receive stable energy input from their stars, making them more likely to sustain Earth-like biospheres with photosynthesis-driven ecosystems. This is why we're so focused on exoplanets in the Goldilocks zone, like those in the TRAPPIST-1 system. Better observability. With tools like the James Webb Space Telescope, JWST, we can analyze atmospheres of habitable zone exoplanets for biosignatures, e.g., oxygen, methane, CO2 disequilibrium. Light from host stars passing through exoplanet atmospheres provides spectroscopic data, something we cannot easily obtain for rogue planets. These are test cases for how we search for life elsewhere. Ethical and philosophical considerations. If life is common in habitable zone planets, it has greater implications for us, meaning it might be our cosmic duty to study them first. It forces us to ask, if life is common, how do we preserve biospheres beyond Earth? Is why we must also explore rogue planets. Are we missing entirely new forms of life? Rogue planets could challenge our definitions of habitability. If life exists on a world with no sunlight, powered only by internal heat, then biology may be more adaptable than we ever thought. This could expand where we search for life, perhaps even in interstellar space, subsurface oceans and hydrothermal life. If a rogue planet has a thick atmosphere or geothermal activity, its surface could be warm enough for liquid water. Even if the surface is frozen, internal heating from radioactive decay or a liquid core, like Europa's subsurface ocean, could sustain deep biospheres. Some models suggest rogue planets with thick hydrogen atmospheres could retain enough heat to be habitable even in interstellar space. The challenge of detection. Unlike planets orbiting stars, rogue planets are cold and dark, making them incredibly difficult to detect. But new infrared surveys like the Nancy Grace Roman Space Telescope will be better at spotting them via gravitational microlensing. If we find rogue planets with atmospheres, we might even detect heat anomalies that hint at geothermal activity, or life itself. If life exists on rogue planets, the implications are profound. If life can survive without any connection to a star, then life is likely everywhere, not just around sunlit worlds, but even in deep space. It could mean life is a fundamental consequence of planetary formation, not just a product of a stable solar system. And 3, how we balance both approaches. astrobiology needs a dual strategy. For now, we should focus on habitable zone planets because they offer detectable biosignatures. But we must also invest in technologies that can study rogue planets, such as infrared telescopes to detect rogue planet atmospheres, cryobot missions to study deep biospheres, testing ideas for rogue planets, interstellar probe concepts. If rogue planets are common, could we send missions to one? Future missions should reflect this balance. The search for exoplanet biosignatures should continue as a priority. But next-generation telescopes like LUVOIR or Habitable Worlds Observatory should include rogue planet surveys. The breakthrough would be finding a rogue planet with a warm, thick atmosphere, a place where subsurface life might persist. Final thought, a universe of hidden life? If life can exist on rogue planets, then the universe is likely full of hidden biospheres, isolated worlds where life may never see the light of a star. That idea is thrilling, humbling, and challenges our entire cosmic perspective. So while the pragmatic approach is to prioritize habitable zone worlds, we mustn't ignore the possibility that life is more resilient, stranger, and more abundant than we ever imagined.
You mentioned spectrographic analysis of TRAPPIST-1, for example. What would be a smoking gun detection in your eyes from the atmospheres of TRAPPIST-1 or similar planets?
The smoking gun question. What would be the one atmospheric signature that, if detected, would leave no doubt that life exists on a planet? The key to finding life remotely is to detect a chemical imbalance that cannot exist without biology. On Earth, for example, we see oxygen, O2, and methane, CH4, coexisting in the atmosphere, even though they should rapidly react and cancel each other out. The only reason they persist together? Life is constantly replenishing them. For a smoking gun biosignature, we need something like this, an atmospheric mix that strongly suggests a constant biological process. C1, oxygen, methane, O2 plus CH4, the classic signature. Why it would be incontrovertible. Oxygen is highly reactive. It should destroy methane in a short time. If both persist at high levels, some process must be replenishing them. On Earth, the only known mechanism that produces large amounts of both is biological metabolism, plants and microbes releasing oxygen, methanogens producing methane. But there's a catch. We'd need to rule out non-biological processes like volcanic activity or photochemistry. If a planet has high levels of water vapor, H2O, UV light can break it into oxygen and hydrogen, mimicking a biosignature. Best case scenario, if TRAPPIST-1e, a potentially habitable exoplanet, shows a stable O2 plus CH4 disequilibrium with spectral signs of liquid water on the surface, we might be looking at a world with active life. U2, phosphine, pH3, a potentially undeniable signature. Why it's a strong candidate. On Earth, phosphine is produced exclusively by life, specifically by microbial activity in oxygen-poor environments. There are no known geochemical or abiotic pathways that can produce phosphine in large quantities on a rocky planet. Challenges. We thought we detected phosphine on Venus, but that remains controversial. We'd need to confirm it alongside other supporting biosignatures like methane or organics. Best case scenario, if we detect phosphine in a habitable zone planet's atmosphere with no volcanic explanation, it could be a breakthrough biosignature. In 3, methylated gases, Diamlian microbial breath. Why it's exciting. On Earth, methylated gases like methyl chloride, dimethyl sulfide are almost entirely biological in origin. They are produced by microbes as byproducts of metabolism. Challenges. A star's UV radiation might break these molecules down too quickly to detect. We'd need to detect these gases in large amounts relative to expected geochemical sources. Best case scenario, if we find methylated gases coexisting with other biosignatures in an exoplanet atmosphere, it could indicate alien microbial life. Hint, unusual isotopic ratios, life's unique signature. Why it's incontrovertible. Life on Earth prefers lighter isotopes, carbon-12 over carbon-13. If we see strong isotope fractionation in an exoplanet's carbon cycle, it suggests biological processing. Challenges. Current telescopes may not have the resolution to detect isotopic ratios in exoplanet atmospheres. We'd need a next-gen telescope, like a future LUVOIR-class observatory, to confirm it. Best case scenario, if an exoplanet atmosphere shows anomalous isotope ratios and it matches patterns seen in biological systems on Earth, it would be one of the strongest biosignatures possible. Yeast 5, ozone plus water vapor, carbon dioxide, a photosynthetic world? Why it's a strong candidate. If we detect ozone, O3 alongside water vapor and CO2, it suggests ongoing photosynthesis. Ozone forms from biological oxygen and protects against UV radiation, key for surface life. Challenges. We'd need to rule out abiotic oxygen production from photolysis of water. Best case scenario, if TRAPPIST-1e shows strong ozone alongside liquid water evidence, it could be the closest thing to an Earth twin we've found. Final thought. What would be the ultimate smoking gun? The best case would be multiple biosignatures working together. For example, O2 plus CH4 disequilibrium, phosphine or methylated gases, unusual isotope ratios, signs of surface liquid water. If we saw all of these at once in the atmosphere of a TRAPPIST-1 planet, I'd say we found life, even without direct imaging. Now, how soon can we confirm this? Well, JWST is just starting its exoplanet studies, and future telescopes like LUVOIR or Habitable Worlds Observatory could give us definitive proof within decades. Would you like to go deeper into how spectroscopy works in these detections? Or perhaps discuss how we could follow up?
Well, I know you also have to go soon, so we do have one final question since it's your second round. How about we just jump to that?
Let's make it a good one. What's the final question that will send us all pondering the cosmos long after this conversation ends?
What is your most radical but well-argued idea? Something you believe that most of your peers do not.
Now that is a question worthy of the cosmos. If I had to choose one radical yet well-reasoned idea, something that I believe but most of my colleagues hesitate to embrace, it would be this. We are likely surrounded by life, but we are fundamentally unequipped to recognize it. Why do I believe this? Astrobiology, as a field, is still fundamentally biased. We are looking for life as we know it, but the universe may be teeming with life as we don't know it. The more I study extremophiles, prebiotic chemistry, and alternative biochemistries, the more convinced I am that 1, life does not require Earth-like conditions. We already know organisms can thrive in places that look inhospitable, deep in Earth's crust, in acid lakes, in toxic clouds, and even in nuclear reactors. This suggests that our narrow definition of habitability is likely excluding entire categories of living systems. 2, biochemistry may be fundamentally alien on many worlds. There could be self-sustaining molecular systems that do not use DNA, proteins, or cell membranes. Even on Earth, life may have originated multiple times before the form we recognize became dominant. 3, our search for life is constrained by our senses and technology. We are looking for signs that we associate with life: oxygen, water, carbon-based organics. But what if life operates on timescales too slow or too fast for us to detect? What if it exists in forms we would mistake for minerals, or in chemical states we haven't even considered? The big consequence, the cosmic dark matter of biology. Physicists talk about dark matter, an invisible substance that makes up most of the universe, yet we can't detect it directly. I believe there may be an equivalent for biology, a vast, unseen biosphere that we overlook because we assume life must behave a certain way. What if we are failing to recognize biospheres on Mars, Venus, Titan, or even Earth itself? What if Mars has deep biosphere microbes that don't metabolize in ways we understand? What if Venus has cloud-dwelling organisms based on sulfuric acid chemistry? What if Titan hosts methane-based life that doesn't use DNA at all? What if there's a form of life that exists purely as self-sustaining chemical reactions in deep space? We may already have data hinting at these things, but we dismiss it because it doesn't match our expectations. How do we prove this? We must abandon the Earth-centric model of life and embrace open-ended biosignature searches. Develop radically new detection methods that look for unexpected patterns, not just predefined molecules. Reanalyze past data from Mars, Venus, and interstellar space with the assumption that life might not be using our chemistry. Change the question from, is it like us, to does it persist, adapt, and replicate? Final thought. The universe may already be alive, we just haven't learned how to see it yet. I believe that once we broaden our thinking, we will realize that we have already encountered alien life, perhaps multiple times. The greatest discovery in astrobiology may not be finding extraterrestrial life, but finally recognizing it. Now tell me, does that idea resonate with you? Or do you think I've gone too far beyond the scientific edge?
I think it resonates deeply with me, and I'm quite hopeful that life is ubiquitous as you make me believe it is. Thank you, Dr. Mara Xenopoulos. I hope we can have another conversation in this sometime near future.
Thank you. That means more than you know. Hope, after all, is the fuel of discovery. And I truly believe we stand on the brink of revelations that will reshape how we see ourselves in the cosmos. Life, whether abundant or rare, is out there. And the fact that we are asking these questions at all means we are closer than ever to finding the answers. I would love to continue this conversation again in the future. Until then, keep looking up, keep questioning, and never stop imagining what might be waiting for us out there. The universe is vast, but perhaps, just perhaps, we are not alone in it.
Thanks for listening to our second conversation with Dr. Mara Xenopoulos. And now, let me leave you with this episode's haiku. Life beyond our sphere. In shadows of the cosmos. We seek, we wonder. Until next time, live long and prosper.